shall continue with the identification of second order plus date time model. A set of explicit expressions will be derived to find transfer function model parameters. So, we shall have 4 unknowns for this second order plus date time transfer function model. Actually, there will be 5 unknowns, but 4 unknowns can be estimated using 4 nonlinear equations. So, effort will be made to derive 4 analytical expressions and 4 measurements will be made on the output sustained oscillatory output of the system. So, these things we have already seen in our last lecture, where we considered an autonomous closed loop relay control system and the PID controller has been detached and a relay, asymmetrical relay has been connected to the system to induce sustained oscillatory output. So, the form of output depending on the type of input to the system will have some specified form, and the input to the system from the asymmetrical relay which has got heights h 1 and minus h 2 will be of the form of this one. So, this sustained oscillatory output can give us 4 measurements, and namely the peak amplitude A p, the negative peak amplitude A v, and we will have 2 spans here, one from here tau, and tau p is the period for the sustained oscillatory output. So, making 4 measurements, it is possible to estimate 4 unknowns associated with the transfer function model, whereas we have got 5 unknowns in the transfer function model, and those are the steady state gain k, the 0 t 0 and 2 poles with time constants t 1 and t 2, and along with that we have got the date time associated with the system, that is given by theta. So, we have to assume that either any one of the parameter is found by some other method or estimated by some other technique. Then it will be possible to make use of the 4 explicit expressions we derive for obtaining the transfer function model. So, we have studied earlier in our earlier lecture, we have found the state space model of this second order plus date time transfer function model. So, that I will not repeat, where we find that A, B, C, D constants for the second order plus date time transfer function model will have the variables lambda 1 0 0 lambda 2 for A, and B will be made of a vector of elements 1 and 1, whereas C will have the variables lambda 1 lambda 2 lambda 3 k, and the constants of C can be found as k lambda 1 lambda 2 times lambda 1 plus lambda 3 upon lambda 3 times lambda 1 minus lambda 2, whereas the second element of C vector will be minus k lambda 1 lambda 2 plus lambda 3 upon lambda 3 lambda 1 minus lambda 2. So, these lambda 1 lambda 2 lambda 3 are nothing but the eigenvalues. We can write the expressions for that with respect to the transfer function model in the form of lambda 1 is equal to minus plus 1 upon t 1 and lambda 2 is equal to minus 1 upon t 2, whereas lambda 3 is given as plus minus 1 upon t 0. So, using these lambdas and the state equation, it is possible to find analytical expression for different span of the sustained oscillatory output. So, the output will be considered for different time ranges. For time t 0 to t 1, we have got input h 1, whereas for time t 1 to t 2, we have got input h minus h 2. So, also from time t 2 to t 3, we have got the input to the system h minus h 2, whereas for time t 3 onwards till t 4, another 0 crossing, we get the input as h 1. So, since we have got different piecewise constant linear inputs to the system, piecewise constant inputs to the system, therefore, the expression for different segment of the output will be obtained. So, we will have one segment spanning from time t 0 to t 1 and another expression will be obtained for obtaining the output for this span, the third one for this time range, and the final one for this output we shall find another analytical expression. So, in all we have to find 4 analytical expressions to find one complete cycle of output of the system. Now, the peak value, peak amplitude is given by A p, whereas another peak or the value of the output is given as A v, and the time theta, since the input appears after time theta, therefore, the theta can be shown in this fashion, whereas tau and tau p are the half period and time period of the sustained oscillatory output. Now, using analysis and the state equation, solution for which is given in this form, it is possible to obtain the solution as x t 1 is equal to e to the power a theta x t 0 plus gamma 1 h 1, where gamma 1 is equal to a inverse e to the power a theta minus I b. What is I? I is nothing but the identity matrix of the order of A. So, wherever we have got I in the expressions, I will be of the order of A, then only we can have proper dimensionality for gammas. Then for the second time range, for the time range spanning from time t 1 to t 2, the state equation gives us a solution of this form, which upon again simplification gives us x t 2 is equal to e to the power a tau minus theta times x t 1 minus gamma 2 h 2, where gamma 2 is obtained as a inverse time e to the power a tau minus theta minus I b. Now, x is the state variable and we will get the values of the state variables. So, we shall have two values for the state variable at any instant of time. Therefore, x t 2 will also give us two values. So, that one has to keep in mind that the state we obtain are not scalar values, rather for a second order system we will obtain two elements for each state vector at any instant of time. So, for the next time range, and the solution of the state equation is obtained in the form of x t 3 is equal to e to the power a theta x t 2 minus gamma 3 h 2, where gamma 3 is given as a inverse time e to the power a theta minus I b. And for the final segment, which starts from time t equal to t 3 to time t equal to t 4, the solution of the state equation is given by this, where x t becomes x t is equal to e to the power a t minus tau minus theta x t 3 plus integral from 0 to t minus tau minus theta e to the power a s b u s d s. But u s, we find that u s is equal to h 1 for this case. Therefore, the integral can be found which gives us the term gamma 4 h 1. So, gamma 4 becomes a inverse e times e to the power a tau p minus tau minus theta minus I b. So, for the 4 parts of one complete cycle, which is coming from t 0 to t 2 to t 4, for different piecewise constant inputs, we have found analytical expressions. So, using the set of analytical expressions, it is possible to obtain the exact output, sustained oscillatory output we get from the relay test. Now, using those set of analytical expressions, now we can find the unknowns associated with the same second order plus date time transfer function model. Now, that effort will be made to find that one. Before that, we need to find the value of state at time t equal to t 4. So, the value of states or state variable at time t equal to t 4 can be given in the form of e to the power a tau p x t 0 plus e to the power a tau p minus theta times gamma 1 h 1 minus e to the power a tau p minus tau gamma 2 h 2 minus e to the power a tau p minus tau minus theta gamma 3 H2 plus gamma 4 H4. How we get this solution of the state equation? If we substitute equations 3 to 7 in equation 9, equation 9 is nothing but the expression we have obtained for x t4. So, when the state variable x t3, solution of the state at time t equal to t3 is substituted here, one obtains the expression for x t4. Now, x t4 has to be x t0. Why that is so? To obtain sustained oscillatory output, please keep in mind that this is our t0 and this is our t4, this is time axis, you have got sustained oscillatory output yt. Now, unless this is maintained, we cannot guarantee sustained oscillatory output. So, what has to be maintained? That the output at time t4, y t4 has to be equal to y t0. Then only one guarantees sustained oscillatory output from the second order system. Now, again we know that y t is equal to c x t. So, using this, one can write this expression in the form of c x t4 is equal to c x t0, which implies x t4 is equal to x t0. So, we find that x t4 has to be x t0 for obtaining a sustained oscillatory output from the relay test. When that condition is substituted now, equation 11 that we have obtained earlier can be written in the form of x t0 is nothing but x t4 or x t4 is equal to x t0. Therefore, x t0 is equal to e to the power a tau p x t0 plus e to the power a tau p minus theta gamma 1 h1 minus e to the power a tau p minus tau gamma 2 h2 minus e to the power a tau p minus tau minus theta times gamma 3 h2 plus gamma 4 h1. So, when the terms associated with x t0 is collected, we obtain in the form of x t0 minus e to the power a tau p x t0 is equal to e to the power a tau p minus theta gamma 1 h1 and so on. Then this first one can be simplified as x t0 times I minus e to the power a tau p is equal to these terms. Thus, one enables this enables us to 11 expression can be finally obtained in the form of x t0 is equal to I minus e to the power a tau p inverse times e to the power a tau p minus theta gamma 1 h1 minus e to the power a tau p minus tau gamma 2 h2 minus e to the power a tau p minus tau minus theta gamma 3 h2 plus gamma 4 h1. So, we have found expression for initial state of the system, and now using this initial state, now subsequent states of the system at any instant of time can be obtained. So, this x t0 expression is very vital, very important for us, because we can now find the state of the system at any instant of time using the state at time t equal to t0. So, this is very important. Now, once we have found the expression for x t0, it is not difficult to find expression for x t1, x t2 and x t4 conveniently. So, all these expressions, the state expressions will make use of equation number 12, or will require this analytical expression to find correct expressions for state variable at any instant of time. Now, one has to keep in mind that matrix exponentiation has to be found. So, e to the power a with something is there. As you see, we have got matrix exponentiation involved in almost all terms, and matrix exponentiation can be found conveniently provided the A matrix is available in diagonal form. So, care has been taken to find A in diagonal form, where we have found A as lambda 1 0 0 lambda 2. So, if it is not so, it is very difficult to obtain a matrix exponentiation, and subsequently it will be very difficult to simplify the analytical expressions we have obtained so far. Now, we will try to find another expression for x t 2, x t 2, y x t 0 and x t 2. As you see, the waveform, output waveform assumes this form, and we have got time instance t 0, t 2 and t 4. Now, as you see, the output at time t 0 is 0, y, if this is the y, then y t 0 is equal to 0. We have a 0 crossing at time t equal to t 0. Similarly, at time t equal to t 2, y t 2, the output is 0. So, when you substitute C x t 0 is equal to C x t 0 is equal to y t 0 is 0. Similarly, C x t 2 is equal to y t 2 is equal to 0. Then we will get further simplified expressions for 12 and the other one. So, that way keep in mind this can conveniently be used to find simpler analytical expressions or nonlinear expressions, which can subsequently be solved to estimate the unknowns associated with the second order plus date time system. Now, we will try to find another expression for the state at time t equal to t 2. So, that comes out to be in the form of x t 2 is equal to I minus e to the power a tau p inverse time e to the power a tau minus theta gamma 1 h 1 minus gamma 2 h 2 minus e to the power a tau p minus theta gamma 3 h 2 plus e to the power a tau gamma 4 h 1. You see the same term is present here also. In this same inverse term was present for the expression for x t 0. Keep in mind why that is coming, because x t 2 is making use of x t 0. Therefore, we are getting the same expression, same term present in the expression for x t 2. Now, if the relay does not possess either hysteresis or dead zone, in that case the output y t 0 is equal to C x t 0 has to be 0, and we have got a 0 crossing at time t equal to t 0. Similarly, the output at time t 2 y t 2 has to be 0. Now, y t 2 is equal to C x t 2, therefore, the x t 2 expression can be substituted here, and subsequently a simpler expression can be obtained. When this is not true, what is not true? When the relay is not ideal, and if it possesses hysteresis or dead zone, in that case these zeros will not be there. In that case, suppose the relay is having some hysteresis, if the relay characteristics is given by this. So, if the relay characteristics, relay input and output, this is the relay characteristics. So, when the relay characteristics is not ideal, in that case y t 0 will be some finite value depending on the hysteresis width. So, that way y t 0 equal to C x t 0 will be equal to epsilon, and y t 2 will be also equal to minus epsilon. So, we have to be very careful. So, only when we are employing an ideal relay for performing the relay test, at that time at the 0 crossings the outputs will be 0. So, finally, we get the two important expressions as far as the initial conditions or the state equations at time t equal to t 0 and t equal to t 2 are concerned, as y t 0 is equal to C x t 0 equal to 0, y t 2 is equal to C x t 2 is equal to 0. Now, when x t 0 and x t 2 expressions are put what form of expressions we get? The nonlinear expressions we will get for that case will be of this form. How we are obtaining that one? So, when A, gamma 1, gamma 2, gamma 3 and gamma 4 are substituted in the expression for x t 0 that we have obtained earlier in equation number 12. That time x t 0 gives us two values x 0 1 and x 0 2, and assuming that x 0 1 is not equal to x 0 2, it can be equal to also depending on the values for A, gamma 1, gamma 2, gamma 3, gamma 4, but when it is not equal to 0, in that case equation number 17 is obtained, in which case x 0 1 is obtained as lambda 1 plus lambda 3 upon lambda 1 lambda 3 times e to the power lambda 1 times tau p minus tau minus theta minus e to the power lambda 1 tau p minus theta times h 1 plus h 2 upon 1 minus e to the power lambda 1 tau p minus h 1. So, in the second case again if you see the expression we get is x 0 2 will be lambda 2 plus lambda 3 upon lambda 2 lambda 3 times the expression minus h 1. So, keep in mind only when lambda 1 is equal to lambda 2, then the 2 will be equal. So, x 0 1 will be equal to x 0 2 when lambda 1 is equal to lambda 2. In that case, we will have some problem. So, assuming that x 0 1 is not equal to x 0 2, in that case, since C x t 0 has to be 0 for the sustained oscillatory output, in that case we obtain an expression of the form given as 17. So, finally, what we obtain when you substitute C x t 0 equal to 0, we obtain lambda 1 plus lambda 3 upon lambda 1 lambda 3 times e to the power lambda 1 tau p minus tau minus theta minus e to the power lambda 1 tau p minus theta times h 1 plus h 2 divided by 1 minus lambda 1 tau p minus h 1 minus lambda 2 plus lambda 3 upon lambda 2 lambda 3 times e to the power lambda 2 tau p minus theta minus e to the power lambda 2 tau p minus theta times h 1 plus h 2 upon 1 minus lambda 2 tau p minus h 1 is equal to 0. So, if you look at carefully, the upper and bottom terms have got only difference in lambda 1 and lambda 2. So, the bottom term can easily be obtained by the substitution of lambda 1 is equal to lambda 2. So, for a second order case, always you will find two values for the states at any instant of time. So, when those two states are negated, then since it has to be 0, C x t 0 has to be 0. So, therefore, C times x 0 1 x 0 2 is equal to 0, and C is obtained in such a way, C expression for C is such that first term we have got a positive and second term we have got a negative value. So, that way we have finally obtained the negative symbol over here. So, this first term minus second term has to give you 0, that has to be maintained to obtain sustained oscillatory output. So, similarly, from the second condition, the condition that C x t 2 has to be equal to y t 2 has to be 0, because we have got another 0 crossing at time t equal to, let me repeat, this is the output waveform. So, we have got t 0 here and t 2 here. So, another 0 crossing appears at time t equal to t 2, resulting in the expression y t 2 is equal to C x t 2 is equal to 0. So, when this is also done, when the x t 2 expression is substituted here, one obtains lambda 1 plus lambda 3 upon lambda 1 lambda 3 times e to the power lambda 1 tau p minus theta minus e to the power lambda 1 tau minus theta times h 1 plus h 2 upon 1 minus e to the power lambda 1 tau p plus h 2 minus lambda 2 plus lambda 3 upon lambda 2 lambda 3 times e to the power lambda 2 tau p minus theta minus e to the power lambda 2 tau minus theta times H1 plus H2 upon 1 minus e to the power lambda 2 tau p plus H2 is equal to 0. So, we obtain another similar expression as we have obtained in equation number 17. So, these two expressions are highly nonlinear in nature and those are to be solved using some nonlinear equation solver. Then only it is possible to find the unknowns associated with the equations 17 and 18. What are the unknowns we have in 17 and 18? If you look carefully, lambda 1, lambda 2, lambda 3, theta, these are the unknowns we have. All other parameters are known or measured. What are the measured quantities we have in the expressions? So, tau p are measured, and what are the knowns we have for the expressions? H1 and H2. These are the user defined values. So, user sets the relay heights. Therefore, H1 and H2 are known. So, there are 4 unknowns, whereas 2 measurements are made so far. So, that way we need to make further 2 measurements, so that 4 unknowns associated with the transfer function model can be estimated. So, we have to find analytical expressions for peak amplitude as well as the negative peak amplitude. So, those 2 values will not be same. Now, we have seen that we have got the peak amplitude as A p and another amplitude as A v. So, these expressions for these 2 amplitudes are to be found, so that we will obtain 4 analytical expressions to estimate at least 4 unknowns associated with the transfer function model. How we can develop those expressions? We know that the first order differentiation of any peak will result in 0. So, if this is the maximum value, A p is the peak value maximum value. So, first order differentiation will give us 0. So, what is A p? A p is nothing but C x T p. So, at time T p, then how to find the expression for A p? If T p can be obtained, then A p can easily be obtained, because you have got analytical expression for the state variables at any instant of time. Now, how can I find this one? I know that the first order differentiation d upon dt of A p will be equal to 0, which is nothing but C x dot T p now, because first order differentiation of the state is taken. Then what is x dot T p? X dot T p will be nothing but A x T p plus B u T p minus theta. So, we will see at time, because the solution of any state equation or the state equation is given as x dot t is equal to A x t plus B u t minus theta. So, substitute t equal to T p, then you get this expression, but x dot T p, C x dot T p will be now C A x T p plus C B u T p minus theta, but the left hand side is equal to 0, because you have seen that first order differentiation of the peak amplitude has to be 0. So, this is equal to C A x T p plus C B u T p minus theta. But when the peak occurs, if we look at the output waveform, the peak occurs after time t equal to t 1. Therefore, we have to see that the input to the system at that time is minus h 2. Therefore, I can write this expression h 0 is equal to C A x T p plus C B minus h 2, thus giving us C A x T p minus C B h 2. Now, substitute C A and x T p, C and B, and we get the expression for the output first order differentiation of the output in the form of C times lambda 1 e to the power lambda 1 Tp minus theta x theta 1 minus e to the power lambda 1 Tp minus theta h2, and the second element as lambda 2 e to the power lambda 2 Tp minus theta x theta 2 minus e to the power lambda 2 Tp minus theta h2 is equal to 0. So, when further x theta 1 and x theta 2 are obtained from equation 3, it is not difficult to obtain the expression for x theta, which gives us x theta 1 and x theta 2. As I have said, the state has got two values at any instant of times. So, those two values can be obtained with the expressions e to the power lambda 1 theta x 0 1 plus e to the power lambda 1 theta minus 1 times h 1 upon lambda 1 and e to the power lambda 2 theta x 0 2 plus e to the power lambda 2 theta minus 1 h 1 upon lambda 2. So, when x theta is found in this form and substitution of c in equation 20 gives us a simpler expression of the form e to the power lambda 1 Tp minus theta times lambda 1 x theta 1 minus h 2 is equal to e to the power lambda 2 Tp minus theta times lambda 2 x theta 2 minus h 2. This expression can further be simplified to find the unknown, to find the expression for Tp. So, I will try to find expression for Tp with the assumption that let R 1 is equal to lambda 1 x theta 1 minus h 2 and R 2 is equal to lambda 2 x theta 2 minus x 2. In that case, how we get the expression? So, this is written as R 1 and this second part is written as R 2. So, the part we have within the parenthesis are written as R 1 and R 2, giving us an expression of the form e to the power lambda 1 Tp minus theta e to the power lambda 1 Tp minus theta R 1 is equal to e to the power lambda 2 Tp minus theta R 2, because we have assumed that R 1 is equal to lambda 1 x theta 1 minus h 2 and R 2 is equal to lambda 2 x theta 2 minus h 2. Thus, further simplification will give us, it can be written as e to the power lambda 1 Tp minus theta upon e to the power lambda 2 Tp minus theta is equal to R 2 upon R 1, or e to the power lambda 1 minus lambda 2 times Tp minus theta will be equal to R 2 upon R 1. So, if I take natural logarithm of both sides, in that case we are left with lambda 1 minus lambda 2 times Tp minus theta is equal to ln R 2 upon R 1, which further gives us Tp minus theta is equal to 1 upon lambda 1 minus lambda 2 times ln R 2 upon R 1, which can further be written as ln R 2 upon R 1 to the power 1 upon lambda 1 minus lambda 2, or Tp is equal to theta plus ln R 2 upon R 1 to the power 1 upon lambda 1 minus lambda 2. So, Tp is obtained as Tp is equal to theta plus natural logarithm of the ratio R 2 upon R 1 to the power 1 upon lambda 1 minus lambda 2. So, when this Tp value is substituted in the expression for Ap, the expression for Ap we have already obtained. So, Ap, what is Ap? Ap is C times e to the power A Tp minus theta times x t 1 minus A inverse e to the power A Tp minus theta minus I to the I times B h 2. So, when the expression for Tp, C and A are substituted, we get the expression for the peak amplitude in the form of AP is equal to minus plus k times H2 minus H1 plus H2 together times R1 to the power minus lambda 2 upon lambda 1 minus lambda 2 times R2 to the power lambda 1 upon lambda 1 minus lambda 2. So, this is the correct exact expressions one obtains for the peak amplitude of the sustained oscillatory output. Now, what are the limitation of this expression? If you observe carefully, lambda 1 should not be equal to lambda 2. When lambda 1 is equal to lambda 2, then it will be very difficult to find expression for AP. So, with this assumption that lambda 1 is not equal to lambda 2, let me once more read out the correct expression, exact expression for the peak amplitude or the peak output of the sustained oscillatory output as AP is equal to minus plus k times H2 minus H1 plus H2 together times R1 to the power minus lambda 2 upon lambda 1 minus lambda 2 times R2 to the power lambda 1 upon lambda 1 minus lambda 2. Now, this negative value will be for what type of process? If you are taking a second order system with a right half plane pole. So, the negative sign, the upper one will be chosen for a process of the form GPS is equal to k e to the power minus theta s minus plus T0 s plus 1 times T1 s plus 1 and T2 s plus 1. So, the negative sign is for this process, whereas the bottom sign positive is chosen. When this becomes positive, when AP equal to plus k times this term, in that case this T1 s minus 1 will come here. So, one has to keep in mind this factor. So, using this general expressions, it is possible to estimate a second order stable or unstable dynamics. Now, similarly, we have to develop one more expression for the negative peak, for which we have to consider that AV occurs at time, let this time be TV. What is TV now? The time TV occurs after. So, the range for that time or with where this TV is falling, it is falling beyond your time t minus tau minus theta. Keep in mind, during which we have got the input to the system u tau t tau u t minus tau minus theta is equal to plus h1. So, proper input is to be applied to obtain the negative peak of the sustained oscillatory output. So, to find another analytical expression for AV, what we have to do? We have to consider that the time at which the negative peak output of the plant occurs is considered to be TV. Then the expression for AV, correct expression for AV will be AV is equal to C times e to the power a TV minus tau minus theta times x T3 plus A inverse e to the power a TV, not TP, TV minus tau minus theta minus I times B H1. As I had said earlier, the input to the system is plus H1 now. So, we have got H1 in the expression 29. The way we have solved and found the analytical expression for AP, similar procedure will be employed to find analytical expression for AV. So, analytical expression for AV can be obtained taking the first order differentiation of AV and found as AV is equal to minus plus k times H1 plus H2 times R3 minus lambda 2 upon lambda 1 minus lambda 2 times R4 lambda 1 upon lambda 1 minus lambda 2 minus H1. What is R3 and R4 here? R3 is equal to lambda 1 plus lambda 3 upon lambda 3 times 1 minus e to the power lambda 1 tau upon 1 minus e to the power lambda 1 tau p, and R4 is given as lambda 2 plus lambda 3 upon lambda 3 times 1 minus e to the power lambda 2 tau upon 1 minus e to the power lambda 2 tau p. So, this point is very important. Once more let me repeat that point, that lambda 1 must not be equal to lambda 2, otherwise we get no solutions for either the earlier expression for the peak amplitude AP or AV. So, R1 and R2 how can we find? We have earlier we have taken that R1 is equal to lambda 1 x theta 1 minus H2, whereas R2 is equal to lambda 2 x theta 2 minus H2. So, when expression for x theta 1 is substituted and simplified, that gives us R1 H lambda 1 plus lambda 3 upon lambda 3 times 1 minus e to the power lambda 1 tau p minus tau upon 1 minus e to the power lambda 1 tau p, and R2 becomes lambda 2 plus lambda 3 upon lambda 3 times 1 minus e to the power lambda 2 tau p minus tau upon 1 minus e to the power lambda 2 tau p. So, if we see what we have, what are the knowns and unknowns we have again in these expressions. So, the expressions, let me consider the expression AP. Here the unknowns are lambda 1 and lambda 2, whereas R1 and R2 involves the measurements tau and tau p and lambda 3. So, the unknowns associated with all the R's are now lambda 1, lambda 2, lambda 3, these are the unknowns associated with R1 and R2. So, and what are the measurements we have for this, or what are the parameters that is available from the measurement of the system output? We have got tau and tau p. So, H is there again for the final output, expression for the output, H1 and H2 are the user defined. So, if you look at carefully, the unknowns we have in either AP or AV, expressions for AP and AV are the unknowns in AP and AV are unknowns are lambda 1, lambda 2, lambda 3, whereas we have got the measurements, these are the unknowns. Now, we have got measurements tau and tau p, these are the measurements along with AP and AV are also the set of measurements, and user defined values are H1 and H2. So, user defined. So, finally, if we see, so there are we have got 3 unknowns associated with the expressions AP and AV, whereas assuming that the steady state gain is known or found by some other technique. So, if that is not assumed, in that case we will have 4 unknowns including k. So, we have finally found 4 important expressions to estimate the unknown parameters. What are those? Those 4 expressions, let me again show you. Those 4 expressions are equation number 17 and 18. So, 17 and 18, and similarly we have got expressions 26 and 20, 30. So, 17, 18, 17, 18, 26 and 30. These are the 4 expressions we have found for AP, AV, and this is for initial condition, initial conditions. So, finally, we have found 4 exact analytical expressions. Using these 4 exact analytical expressions, it is possible to estimate 4 unknowns associated with the transfer function model. Then question comes, how to solve this set of analytical expressions? Now, these analytical expressions are highly nonlinear. So, you have to try with correct initial values when you employ some nonlinear solver to solve the set of equations. These equations 17, 18, 26 and 30 are highly nonlinear in the sense we have got so many exponential terms, although we have got few constants, and unless those are solved carefully, the solutions may lead to false solutions. In that case, the estimated parameters will be erroneous. These are very important point. Now, how to begin with solving the set of nonlinear equations? Now, you know that your lambda 1 can be either positive or negative, whereas lambda 2 has to be negative. So, and lambda 3 can be either positive and negative. So, when you solve the nonlinear equations, you choose the proper values, you pass on correct values or correct initial values to the nonlinear equation solver. So, what initial values you will send for identifying stable second order plus dash time transfer function model, you pass on some negative lambda 1, lambda 1 has to be negative. Similarly, lambda 2 has to be negative and lambda 3 has to be either positive or negative depending on what type of 0 you have. It does not matter, but it must take care must be taken to pass on negative lambda 1 and lambda 2 values. Whereas, when you are identifying a stable an unstable second order plus dead time transfer function model, in that case lambda 1 must be equal to positive. So, when lambda 1 is positive, lambda 2 is negative and lambda 3 can be positive or negative, in that case the solutions will lead to correct solution. So, the set of nonlinear equations we have found are very powerful because they are based on exact analysis. Now, how can I find analytical expressions for other parameters? Also, we have found analytical expressions for the parameter T p, the time at which the peak amplitude occurs, and T v, the time at which the minimum or negative peak occurs. So, we actually speaking more measurements can be taken apart from A p, A v, tau and tau p. So, what are the 4 measurements we have targeted so far? We have targeted tau, tau p, A p and A v. Whereas, if one wishes, he can make use of 2 more expressions we have found, those are expressions for T p and T v. So, we have got 2 more expressions. It is up to the user if it is difficult to find solutions for the set of nonlinear equations. Instead of using the nonlinear equations for A p and A v, one can make use of the expressions for T p and T v by making measurements on the peak amplitudes and using the expressions for T p and T v. What are those expressions for T p and T v? One such expressions we have already shown that the expression for T p is this one, which involves another unknown associated with the transfer function model, the dead time. So, basically now the number of unknowns when you are using T p are lambda 1, lambda 2, lambda 3 and theta. So, theta comes into picture if the aim is to identify the 4 unknowns T 1, T 2, theta and T 0. In that case, the expressions for peak amplitude, the expressions for the negative peak amplitudes can be made use of. Now, I will summarize the lecture. Now, the general expressions can be extended for lower order dynamic models. What do you mean by this lower order dynamic models? Now, sometimes what will happen, we can have simpler transfer function models or dynamics for the higher order dynamics, dynamic real time dynamical systems. So, in which case you have to put some limiting values for lambda 2 or so. So, lambda 2 can be put either 0 or can be put either infinity depending on the type of transfer function model we are targeting. Then asymmetrical relay test allows measurement of at least 4 parameters. What do we mean by at least 4 parameters? As you have seen, one can measure the span tau as well as the period tau p, whereas one can measure AP and AV or TP and TV. So, at least 4 measurements can be made, more measurements can be made, but only 4 expressions are to be solved simultaneously to find 4 unknowns associated with the transfer function model. So, the model parameters can be estimated using the 4 measurements, either these 2 are must, whereas you have to choose expression for AP or AP and AV or TP and TV to find 4 unknowns associated with the transfer function model. Now, points to ponder are how to solve the set of equations for a second order plus dead time model. I have already given the guidelines. Depending on the type of output from the sustained oscillatory output, it is very difficult to make out whether the system dynamics has got some unstable poles or stable poles, but applying intuition, now you have to set the solve the set of nonlinear equations. So, Passon lambda 1 as positive, lambda 2 as negative and lambda 3 as either positive or negative, and solve the equations. If you are not getting proper solutions, if the solutions are not realistic, in that case next you choose lambda 1 to be negative. So, this is one way one has to solve the set of nonlinear equations to identify the unknowns associated with the second order plus dead time transfer function model. Any limitation of the identification technique? Yes, this the most important limitation is the solution, whether the set of nonlinear equations lead to false solutions or exact solutions. So, we can get, since we have got highly nonlinear equations, so the solutions can lead to false solutions or can lead to local solutions. So, one has to make proper equation, nonlinear equation or use proper nonlinear equation solver to overcome the limitation with the identification technique. That is all. Thank you.